Okay, everyone, welcome to this session where we're going to straight line a circuit. And what we've got here is we've got a circuit from your ideal diode worksheet. And what I'm going to do is I'm going to go ahead and I'm going to pick the very last one on that worksheet. I believe that was 3 switches in position 3 and switches in position 3. Okay, I'm going to use red pen to denote the circuit that I'm going to get rid of. I should probably maybe use green to show the one that I want to keep. So let me see if I can find some green marker here. We'll do green for keeps and red for the cut. So green is going to be our keeper. I'm just going to go ahead and I'm going to outline it so that you can see what our keeps circuit is. And then I'm going to use red to show which part of the circuit is gone. This is open. We're not using that. This is gone. These circuits are gone. So is this one. So green should show us, nice and easy, what we're going to keep. Now the goal of straight lining is to use a standard where we always put the battery on the left-hand side and all the components on the right-hand side in order. It's kind of like a game of connect the dots, but for circuits. So here we have the battery, what I would call upside down. We want to change it so that the battery is right side up for starters. And then what we're going to do is we're going to follow out of the top of the battery. And the reason that I do that is because we're all used to writing from top left to right and down the page. It's just naturally easier for us in the American culture to do that. So that's what I do. If you have a different method that works better for you, that's fine. You can go out of the bottom of the battery and you can work your way around. But I think if you start at the top and then you give yourself plenty of space, that's the way that we want to see it. We want a nice spacious drawing so that it's easy to read, spot for notes, spot for measurements or calculated measurements. So that's the idea behind straight lining. I'm going to move this and I'm going to just kind of move it up here so that I have it in my view. And I'm going to show my battery on the left-hand side. And I'm going to leave, just some space over here so that I have room for my measurements. So here's my battery, positive, negative, and I'm just going to play connect the dots. I want my battery to be up, positive up, negative down, so I'm going to switch that around. And I'm just going to follow out of the top of my battery over to components. So here's my node for my parallel circuit, going to my diode and my resistor. So those are the first things that I'm going to draw. And I come out of the top just because we go from left to right, top to bottom. I'm going to come down about 2, over, I don't know, about 6, down about 2. It's not a real good looking thing so far. Maybe I'll use my ruler. So this is our 3K ohms. Over here, I have D3. You can see that I go through a node to the anode of D3. I'm going to draw the anode of D3. And my next thing that I see is a switch 2, before I come to another node. And that was diode 3. I'm going to come together at my other node. And so we just draw that right in. And then here at this node, I go through the anode of D2. I go to switch 1 and R1. So I'm just going to play connect the dots. The whole time I'm looking at it, I have the anode of D2. I have another switch, S1, and I have R1 here. Okay, so I'm just going to go ahead then and I'm going to connect everything. All right, put my ground reference in there, and then I'm going to look for missing information. So my R2 is 3K, but this is R1 down here, so this is 2K. And my battery is 10 volts. So I'm going to go ahead and I'm going to write EA equals 10 volts DC. And I'm going to need my resistance total, my current total, and I'll just go ahead and do my power total since we're doing straight lining. Okay, and over here I'll go ahead and I'll put in R2, I'll do V2, R2, I2, P2. And then down here I'll go ahead and I'll do V1, R1, I1, P1. All right, so that's what I've got. So I know if I go through the positive side, I come to a node. I come to the anode and R2, anode of D3, R2. At the bottom side of R2 and the cathode I come to switch 2. The bottom of switch 2, I come back. Bottom of R2 and switch 2 are connected electrically. Switch 2, R2. From this node, I go ahead and I come through the anode and then the cathode of D2 to switch 1 and R1. Switch 1, R1. And then from R1, I make it to the bottom or the negative side of my battery. So I've successfully straight lined my circuit. I know that the battery's on the left, positive up, negative down, everything else is on the right. Okay, so now I go ahead and I'm going to add some test points. TP1, and I'm just going to forget about switches because they're acting like a piece of wire in this circuit. TP2 below the diode. TP3, this point right here, it's the top of the diode, the bottom of the next diode, and the bottom of the resistor, so I don't have to do any new test points here. And then I'll do test point 4. Okay, so I'm going to go ahead and do TP1, TP2, TP3, TP4. All right, so this is my straight line circuit. I want to show current path using electron flow. And then back to the positive. Then I'm going to write in my knowns. I have written in number 1 that I know my total voltage. Down here I know that my resistance is 2.000 kiloohms. Number 2. Number 3, I know that I have 3.000 kiloohms. Okay, so that's my givens. My current path, that's my straight line. All right. Now I'm going to go ahead and I'm going to start to solve. Okay, I'm in a series circuit. We're going to treat these ideal diodes as goes. Polarities match on both of them, so they're both a go. So in ideal diodes, we're treating them as a piece of wire. Let's not think about that too much. We'll just call it good for the moment. That presents a problem up here. If we treat this like a piece of wire, we're technically shorting out R2. We know that there's a little bit of voltage here, so at any rate. Ideally, then we're going to go ahead and we're going to figure out our resistance total. We know that in a series circuit, we are resistive in nature, and our resistance is additive. So we're going to add our R1 and our R2s, okay? And so our R2 is 3K and our R1 is 2K. So we're going to go ahead and we're going to add those two so that we have our RT as our 4th point. That's going to be 5 kiloohms. All right. That allows us to solve for current total, number 5. So 10 divided by 5 is 2. Question is 2 what? 10 divided by 5,000 kiloohms is going to give us 2 milliamps. Okay, go ahead and check that with your calculator if you want to. Then we've got power. So we just did Ohm's law. Ohm's law is VIR. And Watt's law is PIE. All right. So number 6, I'm going to solve for watt. Our power is going to be our voltage times our current. So our volts times our current is going to give me 20 milliwatts. All right. Now I'm going to be able to take my current and put it everywhere in the circuit because I have a current I have similar current through my whole circuit. So I have the same current at R2 that I have at R1. So my current is always going to be 2 milliamps. So 5, 6, 7, 8. Okay. Now up here, I know that I can take my 3,000 times my 2 millis, and I'm going to get 6 volts even. 3 zeros to the right, 3 zeros to the left is going to balance out at 6 volts DC. That's my 9th step. My 10th step is figuring out power. We know the power is voltage times current, so that's going to be 12 milliwatts, 13 and 14. Okay, down here, again, my volts equals my current times my resistance. So I have 4.0 volts DC. Thanks to Kirchhoff's law, I know that the algebraic sum of all voltages in a closed loop is going to be equal to 0. So we'll cover that another time, but I have 10 volts at my battery and I have 10 volts dropped over here, so they balance. All right, so I know that 6 and 4 is 10, right? My current is the same. My resistances are additive. 2 and 3 is 5. And I know that my powers are also additive, so I would expect 8 milliwatts if I take volts times current. 4 times 2, I get 8. And then if I take the millis, I know that I'm going below into the milliwatts. And just for balance, I have thousands of ohms, so I know that I must have thousandths of watts. Okay, so there's my diagram. And the other thing I need to do is figure out what are my voltage drops. I know that I have 10 volts here, so if I drag this along, I've only touched a piece of wire, So at ground, holding my black lead of my meter on ground, I hit my test point 4, I have 10 volts. So I'm going to do plus 10.00 volts DC. Okay, I'm going to move my lead down. I've moved down a little bit. Okay, I know that I must be subtracting 6 volts. So at test point 3, I should read 4.0 volts. Okay. Yeah, this is ideal now. Everything is ideal, so my volts, I don't have a voltage drop. In the real world, I would have a voltage drop of 0.3 or 0.7 for this diode. I'm treating this diode like a piece of wire. It's perfectly conducting in an ideal situation. So test point 2, I should have 4 volts still. Again, this is ideal a situation. And then if I drop down to test point 1, you can see I have no components in here. So I should be measuring 0 volts if I touch my red lead to my black lead. So I'm going to express that as plus or minus 0.000 volts DC. That is how you straight line and analyze your straight line of your circuit. Okay?